Welcome back, Lambda School machine learning students. This is day 2 of the Machine Learning Mini-Bootcamp. Today I'm going to talk about the tools that are used in machine learning, the programming methodology that is required in order to build machine learning models, and the languages that are preferred within that domain and some of the challenges they have, and the challenges that the languages that aren't like those have, which are particularly interesting. Python, R, and MATLAB are the preferred languages for machine learning development. You can do it in any language, but the cost can be much greater. I have more water today than I did yesterday. Wise. Someone asked yesterday near the question time for me to give some examples of the usefulness of machine learning in the real world. And I said, go ahead and Google it, because it's a beaten to death subject, and it's the essence of pseudo machine learning, or journalistic machine learning, if you will, to talk about what cool applications there are and how machine learning is changing the world today and how machine learning is going to change the world tomorrow. If you're participating in this live stream, you have some indication of what machine learning is capable of, or what it will be capable of. And so I leave it up to you to think about the use cases and the exciting applications. And I leave it up to you to make judgments about which of them are especially powerful and which are not. That said, during the full course, I will have lots of time to opinionate about which algorithms work and which do not work, and why, and what that's going to mean going forward into the future, especially in the context of general all-purpose artificial intelligence, or good old-fashioned AI, GoFi, and what it means for an AI to be able to do a particular job better than a human can. Does that mean it's actually smarter than the human? I will opine about that at a later date. During this mini boot camp, and during the course primarily, I'm going to talk about the mechanics of machine learning. And I don't want to philosophize about it particularly. In fact, the strangest thing that came out of my graduate education was that going into my degree, I loved to philosophize about what it was going to be for. And by the time I was finished with my degree, I found I was unable to speak about any subject that I could not write out on the whiteboard from start to finish with an end result. And that if somebody wanted to say, well, what do you think about quantum computing in the context of, doing radiology analysis for cancer detection? Like, I don't know. I know nothing about the specific implementations of that, and I'm not professionally going to just run my mouth about what it's good for. So what I want to teach you are the technical details, okay? It's easy to read tons of web articles about highfalutin philosophy about AI and machine learning. It will certainly help you in your career to be enthusiastic about that stuff. But I want to talk about, X minus Y equals Z, and the times you have to do that, and how many times you have to do it in order to make the program work. That's the beginning of this talk. What is machine learning? Machine learning is not the Matrix. It's not even Watson. It's not chess software, or Go dominating software, or self-driving cars particularly. Machine learning is arithmetic. It's devising methods to do lots and lots and lots and lots of A times B equals C over and over and over again in order to create a space of numbers that a human couldn't do by hand. And that's why we have it, because 100 years ago, humans were called computers, and they worked in an office building, and they wrote out the solutions to equations so that businesses could use them in their engineering work. And we've invented these machines that can do arithmetic much, much faster than we ever could. And so we've started inventing equations and algorithms that utilize that arithmetic, the fact that it can be performed way faster than a human can in order to produce interesting results. Okay, so how do you implement thousands and thousands of multiplies together at once? You do it with programming languages. We run on these general purpose computers. We use a programming language to create a combination of pure mathematics, which you will see when you read a machine learning article, a written scholarly paper like Hinton's seminal work on the ImageNet Deep CNN, or any other machine learning equation. There will be specific equations in there that are just straight up math equations. And your goal is to figure out how they are simple. When you see them, you will be scared and you will say, this looks complicated. Why did somebody write this math out? Why couldn't they just say what it is? And it's because what they wrote was actually simple. And they want you to figure out what that equation means and then plug it in. But what they don't tell you how to do is how to write out that simple math equation in a programming language to do it again and again and again and again and again and again and again. And I'm not going to dive deeply into this during the mini boot camp, but you will see many math expressions where it says multiply W sub I times B sub I. And that's what the equation says. And what's being implied in that is that I goes from 1 to 10,000. And you could learn that reading the paper earlier or even later. They might not tell you at that point. But that W and B are just numbers. And there are 10,000 of each one of them. And each time the program runs, many times, all the numbers W sub 0 multiplies by B sub 0 over and over and over again in order to produce the results. That's machine learning, okay? I think that's about as far as I need to go with simple arithmetic wrapped up inside of a programming language loop. And it's almost always loops. It's loops within loops. It says, do this 10,000 times. 10,000 times, load 10,000 points and multiply them by 10,000 random numbers. And once you've multiplied them by 10,000 random numbers, subtract the result that you got from the result that you expected to get, and then adjust all the weights by the difference between those two values 10,000 times, and then do that inside of a loop 10,000 times. And when you're finished, you have trained a machine learning model. That's the level of precision I want to drill down to in our class. We're going to have 2 levels of abstraction in the class. The first level of abstraction is going to be, I want you to really understand what's happening mechanically in the system. It's going to be the simplest possible representation each time, because I think I told you yesterday in my graduate studies, I wrote neural networks and support vector machines in C++. And it was hard because if you made a small mistake in your loop, if you multiplied W sub I times B sub I plus 1, one time, everything came down like a house of cards, and it took 50 hours to figure out what went wrong. And so what we're going to do is we're going to take very tiny little representations of the problem. We're not going to do 10,000 loops. We're going to do 4 loops over 6 numbers. We're going to take 6 numbers. We're going to multiply them together. We're going to calculate their difference. We're going to adjust the weights, and we're going to do that 4 times. We're going to say, look, if you got 1.25296, you wrote it correctly. You have written a neural network, which is almost what I have just described verbally. That's when we're going to stop. Okay, we're going to learn a machine learning algorithm to that level of granularity on a very, very simple system. And then we're going to say, all right, not your problem. Somebody has written a more powerful solution using Python already. And we're going to go look at that now. Let's go build the one that does 10,000 loops over 10,000 values, or 10 million loops over 10 million values. And it'll take us much less time because someone's already done it for us. I thought I was done talking about programming and simple arithmetic, but I had a bit more to go. So my next 2 bullets about what machine learning are have to do with classes of mathematics or classes of arithmetic. Calculus. Machine learning is simple calculus and complicated calculus. And we will brush up against the complicated calculus in the program, primarily for the purposes of doing a thing called neural network backpropagation. Okay, and the way that neural network backpropagation works is you know that the rules of calculus say that if your answer is different from your prediction by a certain amount, then you can tweak every value all the way through the neural network based on that difference. But in order to do that, you have to be able to do differential calculus for each pair of values all the way back through the pile. And we're going to learn that. We're going to learn the rules, and we're going to learn why it goes back up through the pile so that you can talk to other people about it. And so that if somebody gives you a new equation, you will know how to add back propagation to that. Okay, but calculus is huge. Calculus is 6 courses of college material, even before you get to like the PhD grade calculus. And we're not going to learn calculus, and we're not going to concentrate on it. I am not going to whip out difficult integration rules. I am not going to cause you to prove Taylor series. I'm not going to do anything that's really difficult in any mathematical space during this course, because math is math. Okay, if you are absolutely bomb at math, then certain topics will be much easier for you in machine learning. But you don't have to have this PhD in mathematics in order to do machine learning at all, especially because of the tools that we're going to talk about in this talk in the next few minutes that have been developed. Okay, so if you're not great at math, that's fine. You have a level of inspiration now in your life that is driving you to learn new things, and that is driving you to capture topics that might have intimidated you before, that might have made you feel like it was time to spin up Netflix instead of get to work. And I was there at one time, and I need a revival. In fact, I'm ready to be on fire because I've been doing computer programming long enough that I'm looking for one of you to inspire me at this stage. That would be great. But take that inspiration and don't be afraid, because my goal, I use this expression almost every time I talk about programming or engineering or science. In my experience, there are 2 kinds of software programmers. Ha ha ha, binary divisions, lol lol, everybody's got shades of everything. Well, that's a fact. But there's a compulsion when talking about difficult subjects, abstract subjects, for some people to make the problem harder as a demonstration of their prowess, okay, which is called for, right? If you're in a challenging intellectual environment, you do have some obligation to prove yourself so that you can maintain your status in that community, okay? Some people do that against people that are not equipped to compete with them, right? So many of you have had teachers who would just talk about stuff that was out in the clouds over and over again, and they didn't care whether you were grasping it or not. They enjoyed seeing you glaze over, all right? And there are teachers and computer scientists and engineers who like to make problems simpler. And I am the latter case. I want to make it simple. I want to make it something that can be described with language that I will see the light of understanding in your eyes, not the glaze of, like, I'm still looking at them, pretending that I'm listening, but I'm not. I don't want that. I want you to go, oh, right, because of this and this. So we'll always try to make things simple. And that's why the requirements, the pre-course requirements for this are not so difficult, which you will see in the future, tomorrow. I'll share with you the final pre-course assignment, which is some calculus and some linear algebra written in Python. And it's not hard, and it's not a lot. And I'm sure that you can take care of it. And then once you submit those 12 unit tests, you can say, I've done everything that I can in order to start a new career. I still haven't finished talking about what is machine learning. I talked about the hard part of calculus. Okay, the simple part of calculus that is present everywhere in machine learning is something called function optimization. That is trying to figure out what point in a group of numbers is the most informative. You've got umpteen zillion numbers sitting in front of you on a spreadsheet, and you go, which set of numbers actually tells me the answer? And the most basic idea in all of calculus, the humble derivative, which is a simple operation that you can do on any function and that is present in every function, whether or not you know what the function is or not, that derivative tells you where the most informative points are. And so all machine learning is based on the idea of finding optimas in derivatives of functions that tell you you found the answer. And we'll talk about that in the first part of the course. We will talk about it tomorrow in detail, and I'll write it out for you. I'll give you examples of it and make that make more sense to you. Okay, and then finally, machine learning is linear algebra. In linear algebra, I talked about yesterday, it's points in space. You're on a number line, it's one-dimensional. There's a point on the number line. This is 8, this is 2. Okay, if you add them together, you take the one that's here and you stick it on to the one that you added it to, and you get 10. Pretty cool. Okay, and that works in unlimited dimensions, 2 dimensions, 3 dimensions, 4 dimensions, 5 dimensions. There are simple rules about the relationships between numbers in various dimensions that inform us about the shape of the data that we're studying. All of machine learning is about what is the shape of the space of the data that we are studying. So we'll talk about that a lot. Every time you build a model, you'll need to know. Every time you prepare your data before it goes into your model, you'll be thinking about linear algebra. And so the last day of the pre-course instruction on Thursday is going to be some linear algebra instruction. We're going to talk about adding two vectors together. The most basic value in linear algebra is a number that is a group of numbers called a vector. So we'll add them and subtract them and move them around, and we'll figure out how long they are, and we'll figure out where they're located with relationship to one another, because these are foundational to machine learning. In the primary coursework, we'll talk about linear algebra at a higher degree of detail for probably about a week and a half or 2 weeks, spread out through the course, and different parts of linear algebra that you're going to want to have a mental model for in order to be successful in machine learning. Machine learning. And I think that the proper term is probably a machine learning model shepherd, or a machine learning shepherd, because the number of people who actually build new models in machine learning, like even today, okay, even go back 10 years, like when I was a student of machine learning, okay, the number of students, the number of academics was this big, and the number of them that actually made groundbreaking contributions were this big. Okay, and today, that's another exponential factor smaller. So there's this many people working in machine learning, and there's this many people studying at an academic level, and there's this many people who are creating new algorithms. You don't need to be one of those people. You can have 10 years or 20 or 30, or you can be like Jeff Hinton. Jeff Hinton, bless him, he's got to be 60 years old, okay? He's created 45 publications about neural networks, and it wasn't until 2012 that everybody went, let's talk about Jeff Hinton's work. Okay, so there's no hurry for you to build a new model. The hurry is for you to capture the ability to use the existing models and describe them to your customers and to your bosses and to your colleagues, and draw pictures of them in ways that build trust. All right, so that's what we're going to concentrate on. So I always tend to talk for about 20, 25 minutes, although I always run long too, because now I've only got 35 minutes left before I do some kind of screen sharing. And I want to talk about the basic tools of machine learning next. And I'm going to turn on a screen share for it once I can figure out where to click. Now I can take a drink because you can't see me. And there's a question that says, is machine learning good for startups or just big companies? There are some really interesting startups that are trying to create novel solutions to problems that haven't been solved before using machine learning. So I would say that, yeah, there are tons of important applications of machine learning in startups. I think that the big companies are the majority of the ones that have actually figured out applications for machine learning at this point. And usually they just have to do with measuring the behavior of tons and tons of anonymous people, like I said yesterday. Okay, I wanted to talk about programming languages. What are the important tools for machine learning? Well, I already talked about the mathematics, right? That's the abstract part of machine learning. But excuse me, um, the literal 100% truth is machine learning is totally useless without programming languages. Okay. So I was telling you just a minute ago, you don't have to have a PhD in mathematics to do good machine learning because there is none without looping, iterative, simple number multiplication, and important API usage in the programming language world. Okay, so the one that we're going to be concentrating on is Python. Everybody in the class is going to learn to program machine learning models and data sets, data visualizations, and remote execution environments in Python. We're going to spend a lot of time looking at TensorFlow, which you can use in other languages. And we're going to do visualization. We're going to do data imports. We're going to build simple models. And then TensorFlow here actually comes next because we're going to use powerful APIs. And then finally, we're going to execute models remotely, which is the holy grail of machine learning. Okay, now how do you do machine learning in Python? Well, it all begins with a library called NumPy. Okay, so you're going to have to figure out how to install Python on your computer. And there's lessons about it at the beginning of the course, and we'll make sure that you all get there. But you're definitely going to learn how to do it. And there's another one called matplotlib. And we're going to learn how to use those really early because NumPy lets us put numbers into lists more easily than in other languages. Say, oh, it's common to say this. Equals np.array, and then 3, 2, 1, right? And then we go plt.plot x. Okay, this works. python.py. Oh, so I didn't activate my virtual env, and I don't have one here, which is risky business. So another thing that we're going to learn about very early is something called virtual environments for Python. And we're going to learn about using pip to install these dependencies. Right, so that popped up and then it went away. So I'm going to go ahead and cat it here. Copy it. Then I'm just going to run the Python interpreter. Oh, I have to do plt.show. I often forget. So I have so many programming languages in my brain. Not only do I have all the machine learning programming languages, but I also have iOS, Android, web programming, server programming, firmware, C and C++. And so unfortunately, it's shameful at my level of senior software engineer. I very rarely know how to do anything off the top of my head because I have a general idea of how to do it in 14 different languages. All right, but the point is, we can draw this picture in Python really easily. But Python's not the only machine learning language that matters. R is actually my favorite. And R does lots of things really well. It's exceptionally good at doing simple stuff like draw me a graph. We'll make it blue, just like Python. Except I made a mistake because I made the color B instead of blue, because remember, I don't remember how to do anything at all. Color blue. Nice. All right, so we're visualizing data in two different languages, and we're not done yet. Okay, so before R and before NumPy, all right, Python was just gaining traction when I was finishing graduate school. And it's not as good at certain kinds of numerical calculations as R or Octave are. But all right. But it has lots of money and effort and time going into it, and it's more modern than either are. So that's why we're doing Python. You should be ready to write solutions in R and Octave if someone asks you to, or to reason about R and Octave code. But you can specialize in Python and you'll have more success. Let's see here. Let's see one. There we go. And in Octave, we can do the same thing, although I went the wrong way this time, didn't I? Let's close it up and fix it. Three, two, one. That's better. All right, so these are the three most important languages for doing machine learning. And we're going to learn how to draw graphs. We're going to learn how to create vectors and read files and use these languages when they are important. But most of the time, we're going to use NumPy. In the not too distant future, it's not the language that you're going to want to use is going to be the one that can reach out and power another computer most easily. And machine learning as an industry is going to be there soon, but it's not there yet. And so you still have to mess around with this stuff on your own computer, but there are other better solutions. Okay. Python are, and this is called Octave. Octave is the free version of a language called MATLAB. MATLAB is the oldest and the most famous of all of the machine learning languages. But the fact that the license for it cost, when I was a student anyway, it was about $800 for someone who wasn't a student, has caused it to lose its fame substantially. Joe Cox says Jupyter notebooks, which are huge, and we are going to play with Jupyter. Google just released a new tool set called Collaboratory recently, and it is a installation-free Jupyter notebook. And so we will be using Jupyter notebooks in the course, but we are going to be using them through Collaboratory, where there's no need for a local installation. There's no need for fiddling around with how to do it. It's just something that you can use for free, which I'll just talk about. Well, let's see. Could just bring it up. Let's see. Yeah, R is my favorite language for manipulating data. It's absolutely the best at twiddling numbers and transforming data. It's much better than Octave or Python is at doing matrix multiplications or slicing vectors, but well, it's not as popular as Python. I wish that Google would have used R. And what's particularly funny is that, so I'm an Apple user. I wouldn't say I'm an Apple fanboy. When I was a graduate student in machine learning, Apple was the de facto baseline. And every academic who was doing artificial intelligence was using an Apple. There were a few that used Ubuntu, and there were approximately none at all that were using Microsoft. Microsoft bought R, basically, 4 years ago or so, and they're building a really powerful Azure cloud platform for running R code. So I may switch back to Microsoft just so that I can spend more time with my favorite programming language, R. Most of my Stack Overflow points are from R. I have a pathetic 3,100 about on Stack Overflow, and they're all from machine learning and R type questions. Let's see here. Oh, so did I bring this window up? Okay, so you can also do machine learning in any programming language. It doesn't have to be R. It doesn't have to be Python. Here's an example of machine learning in JavaScript. This new tool called Propel is written by Ryan Dahl, who's the world famous inventor of Node.js. And this is very promising, okay, because JavaScript is way better at doing visualizations than R or Python or Octave or anyone. JavaScript is the absolute #1 most powerful visualization language on earth. And so when we see the machine learning libraries mature a little bit more, I'm very optimistic that JavaScript is going to become more and more relevant. Can't do f of x times 8, that's weak, you see. JavaScript's going to get very, very relevant, even if you can't multiply f of x times 8. The reason for that is, all right, finally, you can also do machine learning in C and C++. You can do it in Java. Case anecdote, personal anecdote. When I was in graduate school, most of the people who wrote algorithms did them either in C++ or Java. And the people who did them in Java had 10 times slower runtimes than the people who did them in C++. And that matters a lot. Because when you run an algorithm that takes a day to finish, there's a huge difference between 10 days and 1 day. I'm just watching commentary scroll by a little bit. I like Clojure too. I don't know of a real world example of doing it in machine learning yet. And I'm just trying to teach something that's the most relevant. If we have Clojure sidetracks and we build cool projects using Clojure during the development of the course, I will welcome them. You know, Scala is huge, Mark, and Scala is especially huge for big data. I think there's a pretty strong chance the big data coursework is still in development. And someone asked me if there would be another instructor. It's going to be myself and a gentleman by the name of Amit Mangani. Amit is more of an industrial big data specialist. I am more of a kind of low-level artificial intelligence specialist. And there's a pretty strong chance that you will get to do some useful big data work in Scala when that time comes by. All right. So there are requirements for machine learning languages that have led to Python and R and Octave becoming the de facto ones. The most important feature is the one that I was talking about with regards to R a second ago, and that is swift data manipulation. That is, if I want to load some data into my R or into my machine learning programming language, I need to be able to adjust its shape intuitively. I need to be able to modify the shape and the structure and the organization of data using my programming language as though it is the first order ability of that language. And I think that Python comes in second place in that regard. When you use NumPy, you can manipulate and slice and reorder and scale the data matrices that you are loading in. But it's kind of an added on capability. It's something that's been added to the language by NumPy. And basic Python is horrific at doing that. C, C++, they're the fastest programming languages. They are every time, with the exception of assembly, they are always faster at doing large numbers of machine learning numerical calculations than any other programming language. Okay, but the problem is that if you want to multiply W sub I times B sub I 10,000 times in C++, you have to tell it what W sub I is first, and you have to tell it what B sub I is first, and you have to tell it how WI gets multiplied by B sub I. And so building machine learning processes in languages that are not specialized to it takes more time than doing the machine learning part does. And that's why, as an industry, we have settled on R and Python and Octave. So in addition to swift data manipulation, your language needs to have great language tools for loading and visualizing data. For example, you need to be able to read a CSV file without having to teach it everything about a CSV file, which is something that, for example, C++ can't do. You want to load a CSV file, which is the simplest possible representation of data. It's going to take you like 35 lines of code in C++ just to read the CSV file. Maybe that's an exaggeration, but you're going to have 35 bugs in it, and it's going to take you 8 hours to make it work. So you need a language that can just chomp a file for you and put the data where you want it. Once again, that's R, Python, and Octave. You want your language to be fast, which really only C++ is. Now, the benefit to R and Octave and Python is that they're actually running C code. Okay, when you train a machine learning model in Python, if you've built it yourself, I'm sorry. When you train a machine learning model in Python using TensorFlow, it is running C++ code that you can't see. That's as fast as it can be. But if you build it yourself, if you're careless, it won't be able to run C++ code, and it will run very, very slowly. But all languages can take advantage of C++ to run more quickly. All right, finally, the last feature that you want a machine learning language to have is you want to be able to share it with others. You don't want it to be something that has to be built using a special make instruction on your personal machine, and that if you want to be able to share it with your boss or your colleague or put it on the internet, you have to teach people how to build it themselves. So that's another reason that C++ and even Java have been left behind as important machine learning programming languages. So there's a bullet point here that I'm really excited about. Where are machine learning tools going? And this is coming very, very soon. Okay, step one, collaborative and presentational model design. Okay. Jupyter notebooks are really cool. Collaboratory is cooler. All right, so Google has created this awesome new Jupyter notebook framework where you can write docs and describe what you're doing, and then you can write code, run it, get the results injected into your website, and then you can click share and say, hey, bro, check out this cool notebook that I created. And I've never done this before with a group. So let's see what happens. So now you all have access to this. Let's give it a name. Mini. All right, and then you can modify it. You can make your own docs. You can add your own model versions to it. All right, and this is huge. This is the next generation of machine learning, because it's really hard to make progress on this stuff by yourself. Everybody has different levels of specialty, and there's always little details that need to be worked out. Finally, the next step, which we're not quite to yet, is that this piece of code is going to run on, I'm getting a million permission requests, and I'm going to go approve them. So 1 second while you all clicky at me. Clicky. Google Drive, how do I get to them? Oh, give. It's going to take me all night to give access. Okay, so the next thing that's super important that I am going to discover and teach you all how to do in the process of this machine learning course is we are going to find a way using collaboratory or local Python or Jupyter notebooks. I don't care where the code is going to be written. There will be a place where we can say, run this on a massive swarm of Google PPUs. Okay, and this is the real future of machine learning, is being able to create a machine learning model and then train it in a place that has, 100,000 times more computing power than your personal machine. That's going to change the future of machine learning. And that's something that, for example, if you built something that could do that, that would be your career. You would be cemented. All right. That has covered it for my cloud presentation. And I've given you an example of how to do this collaboratory thing. Okay, it's really easy. And we will be doing collaboratory work together. Laboratory. collab.research.google.com. I'm going to paste it in. Give, 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 give. Let me check my YouTube monitor. How do I join the machine learning Slack channel? So, Suleiman, you must apply for the machine learning program at Lambda School's website, which I will be sharing a link for you immediately. Upon following this link and filling out the simple form, you can get added to our Slack group. Your email will be registered, and you'll get the chance to complete all the pre-course work and join the full-time or the part-time or whatever else. Briefly, I'm just looking at the chat logs. Let me check over here. All right. Now, the last part of this instructional period is talking about Python locally. There's a program now called pipenv. You can find it on the interwebs. It used to be that you had to hack together your Python environment, but pipenv presumably has made things better. You can probably install a binary version of this on Windows. If you're using OS 10, you just say brew install. And if you're using Ubuntu, you go through this apt-get install process. I don't see anything about pipenv on Windows. So that will be something that we will work out on the future. It says here Windows is a first-class citizen in our world, but it doesn't say anything about installing pipenv on Windows. Now, when you run pipenv, you get to create a new environment in here. It looks like it's got pretty solid instructions. Yep, pipenv install -- dev. Yep. Now, how do I install other dependencies? You need to have a requirements.txt in there. Okay, I think we're good. Give access a few more times. Well, it failed. So, with an SSL error of all things. So I'm not going to mess with that at the moment. What I have is a method called virtual env installed on my system. And in my history, type this in, source a file called activate, and then it modifies my local terminal. Let me make this bigger. People are going to ask me about that. It modifies my local shell to become mlvenv, at which point if I run Python, it has all the dependencies that I need, which I can install using this program called pip, which is now available. So pip install numpy, that's how you get numpy on your program. We'll talk about all this stuff in the full coursework, but you will need to be able to write some Python code and run unit tests for it in order to finish the pre-coursework, because that's the requirement for doing machine learning at Lambda School. You can write some Python, not hard Python, just some Python. It's got to be able to import some libraries. And then you've got to be able to do some basic calculus, which, I mean, it's real basic, so don't be scared away. And you've got to be able to do some basic linear algebra that's well described. Okay, but you've got to be able to get to this stage, right? Python, x equals 5, 5 times 5. Good. You've got to be able to make a function, def f of x, return x squared, f of 10. Good. All right. This can be done. This can be done even for your pre-coursework in Google's magnificent collaboratory, right? So you could just do it here. You could say def f of x. If you can make it work, of 6. Square of 6 is a fine number, isn't it? It's down there. There it is, 36. All right. So this pretty much summarizes, or rather closes out day 2 of the machine learning course. Today I talked about what machine learning really is and what the tools are that you need to get started with it. There are more tools. In particular, reporting is a huge tool, and we're going to spend a lot of time in the course talking about presenting, discussing, describing, and making easier for your peers and your colleagues and your families and your bosses to understand. Okay, that's a really important part of the whole process, and we will spend a lot of time on it during the actual course. There is an assignment that is for running Python code inside of the new repository for Machine Learning Day 2. It's nothing, okay? Make a file called yourname day2 mlbc.py and return this big number. Okay, send me a pull request for this. Yesterday and today's assignments are not as important for your acceptance into the program as the pre-coursework that I'm going to share with you tomorrow. Okay, the pre-coursework that I will share with you tomorrow is a 2-day assignment that's due before the machine learning full-time or part-time course begins. I believe you have a week to do it. Let's ask actually. Karen, when is the ML coursework due? Yeah, so the reason that I like collaboratory here is because no Anaconda installation is required. If I'm going to run Python locally, I just run it in my terminal like this. Maybe I should be reconsidering that. Maybe I should be using Anaconda, but Anaconda is for running Jupyter, right? And Collaboratory has made Jupyter much easier to get involved with. So at this time, I'm not planning on pushing an Anaconda installation. If we're going to do Jupyter, we're going to do it with Collaboratory. if if we're going to do it locally, maybe that's going to be completely impossible without Anaconda on all your different machines and all your different operating systems. So we shall see. Joe, it sounds to me like if you have Anaconda, you have pipenv, so you're good to go. I also wanted to point out that there was an assignment yesterday. I ended the talk. I was totally run out and totally out of steam, and so I forgot to tell you to create a y.md file and tell me why you want to do this, and send me a pull request for that as well. Yesterday's assignment is also not as fundamental to your acceptance to the program as the assignment you receive tomorrow is. Okay, but if you want to be a full-time machine learning student at Lambda School, you better get used to getting an assignment every day and sending a pull request, because there will be a constant stream of work to do. I will take questions for 5 more minutes. I could go back and answer some questions from yesterday in ML lesson 01, or if it's really important to you, actually go ahead and just repost it. And I'm turning this baby off in 240 seconds. So the class for the full-time machine learning course is 45 hours a week. And I will be essentially available all 45 hours the whole time. But there will be times when I'm doing coursework development or where I'm grading. And so I'll have a fixed set of office hours that will typically be 2 to 3 hours a day on top of the instructional time that we're spending together. What you should expect is that we run an A day, B day approach to education. So on A day, you will get about 3 hours of time with me where I am lecturing and doing QAs and spending time with you talking about the assignments, just kind of fully available and present for everyone. On B days, there will be maybe a half an hour to an hour of that kind of instruction. And then there will be the 2 to 3 hours of office hours every day. So I'll be fully available 15 hours a week plus 15 hours a week of actual lecturing time. And then some of the times I'm just going to have to shut the door and hide, because it's actually really hard to teach 50 people all at the same time when we share the same building, that is the same Slack channel. I don't get very much downtime. All right, everybody. I see a couple more questions maybe coming up. Yeah, I have to shut the door because it's really overwhelming when I receive an infinite stream of questions, and then I want to engage, and then we're going to get to know you personally, and I want to work with you, but I have 17 other questions all stacked up in the queue. I've been teaching at Lambda School now for about 6 months, and I'm starting to get a sense of balance. I'm starting to figure out how much I can teach without burning myself out. And that's why I have office hours. Yeah, Abhinav, we're going to build machine learning models, and we're going to use models from APIs that have already been built. We're going to build simple machine learning models because, as I said earlier, it's much harder to build one from scratch than it is to use it. And you'll be able to contribute more learning how to leverage the ones that have already been made than trying to make your own. The worst thing about building your own machine learning model is after you spend 100 hours constructing it, then you go, did I really build it right? Or is it actually broken? If somebody else built the same one, would it get better results than me just because it would have fewer bugs? Right. It's nice to use the existing libraries. Antonio, the full-time course gets a little bit more attention than the part-time course. The part-time course is 15 hours a week for 52 weeks. So there's really only 780 hours of mandatory time in the program, which means that extra time that you contribute is going to come out of your own full-time overtime pocketbook. Whereas 45 hours over 26 weeks, and we might actually bump it up to 30 weeks, we've been talking about changing it, is 300 more hours, 400 more hours than the part-time class, almost 50% longer, more than 50% longer, in fact. And honestly, you're going to have a harder time being successful if you are splitting your time between a full-time job and learning this material. If you just put down everything else, you dedicate yourself all day, every day for 6 months, then you will come out of the program with like fistfuls of material that you can demonstrate to others that, well, without that same dedication, you're less likely to have it. That's my theory. Thanks, everybody. I'm signing out, and I'll see you all tomorrow to teach you function optimization, level 1.